Hi everyone, welcome to this lecture. In this lecture, we are going to start a new section, which is backpropagation. In this section, we will study how neural network learns, and we will also study how we update the weights of a neural network in order to get the improved performance. Let's see what we are going to cover in this section. So basically in this section, we are going to cover only two topics, but we will cover them in detail. That is the forward propagation and backward propagation. In the section which was introduction to neural network and deep learning, we have some idea what is forward propagation and what is backward propagation. But in this section, we will discuss them in detail. So we know that in forward propagation, we basically calculate the error of the model, that is the neural network. And in backward propagation, we update the weights and in that way, we reduce the error. So forward propagation is used to calculate the error and backward propagation is used to reduce the error. So in this section, when we discuss forward propagation, we will discuss it in detail. That is, we will discuss how we can move from the input layer of a neural network to the hidden layer and how we can form the equations and then from hidden layer to output layer. So we will move in two steps, that is from input to hidden and then from hidden to output layers. And during this movement, we will also learn how to write the equations for the forward propagation and how to calculate the error. In the backward propagation, we move in the backward direction. Since in the forward propagation, we will have an error. Therefore, during backward propagation, our target was to update the weights in order to reduce the error. So during the backward propagation, we will move from the output layer to the hidden layer in the first step, and in the second step we will move from the hidden layer to the input layer, and in both movement we will update the weights. That is, first we will update the weights between the output layer and the hidden layer, and then in the second step we will update the weights between the hidden layer and the input layer. So in this way, in this section, we will discuss both these propagations in detail. So I hope you will enjoy this section. I will see you in the section. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the learning of neural networks in detail. If you remember in the introductory section of a neural network, we also learn that how neural network learns. And we saw that neural network learn in two stages or propagations, and that are forward propagation and backward propagation. But in that section, we discuss them briefly. But in this section, which is totally on the back propagation, we will discuss forward propagation and backward propagation in detail. So this is a neural network which we are going in order to understand the forward propagation and backward propagation. So we will use this neural network. So that is called standard neural network. So it has input layer, it has hidden layer, and it has output layer. So there are I neurons in the input layer. Therefore, we can also call it as ith layer. Similarly, there are J neurons in the hidden layer. So we can call it as jth layer as well. And we have K neuron in the output layer. So that layer is also known as kth layer. So we have input layer, hidden layer, and output layer, or we can say that we have ith layer, jth layer, and kth layer. Now we can see that there is a weight between the input layer and the hidden layer. If you see the subscript in the weight, it is Ji. So I is the first layer and J is the second layer. If we move from I to J, that is in the forward direction, then we are moving from input layer to the hidden layer. So in the weight, the subscript of the hidden layer or the second layer will come first, and the subscript of the input layer will come second. Similarly, if we see this weight, it is Wkj. So we are moving from J to K. K is our final position and J is our initial position if we move from J to K. In that case, the subscript associated with the final layer will come first and initial layer will come second. So it is Ji if we move from I to J, and this weight is Wkj if we are moving from J to K. So that notations are standard. Usually in the literature of back propagation, we saw this kind of abbreviations, we saw this kind of notations. That's why it is known as standard neural network. Okay, now if we see this neuron, the J neuron in the jth layer, we can see that we have written two things on that neuron, that is net J and OJ. And similarly, if we see the output neuron, there are two things written on the neuron, that is net K and OK. So it is net J and OJ, and it is net K and OK. Okay, now what is net J? So basically, net j is the input side of the neuron and oj is the output side of the neuron of the hidden layer. So net j is receiving input from the input layer and oj is the activation function of net j. Similarly, this is our output neuron. So it has two variables associated with that, that is net k and ok. Net k is the input side of this neuron and ok is the output side of the neuron. So what will happen, that net k represent the input which is coming to this neuron and ok is the activation function of that input. Let's see this neuron and this neuron in detail. So basically here we have a neuron, the output neuron. So this is net k and this is ok. If you see net k is at the input side of the neuron. So basically net k is getting all the inputs from the branches which are connected with this neuron. And when we have net k, ok is just the activation of net k. That is, if we have net k and if we have a sigmoid function as an activation function, then after calculating net k, we have to calculate the sigmoid of that net k in order to get ok. So if our activation function is sigmoid, then ok is the sigmoid function of the net k. That is, ok is the activation function of the net k. So that is our standard neural network. We have net j and oj, and we have net k and ok. Now we have clearly understood what does it mean, that net j or net k are the input side of the neurons and oj are the activations of that inputs which we calculated. Okay, let's start forward propagation in detail. So in the first step, we will calculate the equation of neuron j. That is, we will calculate the equation of the neurons which are present in the hidden layer. It means in the first step of the forward propagation, we are moving from input layer to hidden layer. Now let's see how to calculate net j. So here is net j. So what is net j? Net j is the sum of all the w and x1 which are coming from the input layer. Okay, so this is x1 xi and this is wji. So what will happen? This is the input to this hidden layer or the jth layer or the jth neuron. So if I multiply this weight with x, it will become wji and xi. So since we have a large number of neuron or we have I number of neuron in the input layer, therefore we have to take the sum of all the I neuron. So this will become input to the neuron, and also there is a bias associated. So therefore the total input to this J neuron will be the sum of the product of all the weights and the features plus the bias. Okay, after calculating a net J, what is OJ? So OJ is the activation function of net J. So here, if we are using an activation function as a sigmoid, so basically OJ is the sigmoid of a net J. And we know that according to the equation of sigmoid, it is 1 over 1 plus e raised to power minus x. Since here we are calculating the sigmoid of net J, therefore instead of x, we have here net J. So this is the equation for the neuron which is present at the hidden layer. So this is the equation which we obtained in going forward. Now the second step in the forward propagation will be to move from the hidden layer to the output layer. Therefore, now we are going to find the equation of this neuron, which is the kth neuron. So now neuron K. So for neuron K, we have to write first the equation of net K like we did with this neuron, that is the jth neuron. And finally, we will take the activation of net K in order to complete the equation of a neuron K. So if we see here, K is getting input from the hidden layer. So what is the input? So input is the product of the input feature or input which is coming from the jth layer and the weight associated with this. So we have to multiply this. So we have WKJ and OJ. And since we have J number of neurons, therefore we have to take a sum of all the inputs which are coming from the Jth layer to our output layer. And then we have a bias associated with the output neuron. So this is our net K. So net K is the sum of all the inputs which are coming from the hidden layer to the output neuron. So the final step is to find the OK, that is the output of neuron K. And we know that OK is the activation of net K. If we are using a sigmoid as our activation function, then it will be 1 over 1 plus e raised to power minus net K. So in this lecture, student, we learn how to make the equation in the forward direction. We see what is standard neural network. We see the notations used in the standard neural network, and we learn how to move from the input to output through the hidden layer, and how to make the equation for the neurons of the hidden layer, and how to make the equation for the neuron at the output layer. So I hope you understood the concept of a forward path. I hope you understood how to make the equations if we move in the forward direction in the neural network. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn how to perform backward propagation and how to write the equations for the backward propagation. So in the previous lecture, we learned about the forward propagation. So in forward propagation, we move from input layer towards the output layer, and we form the equation both for the neurons of the hidden layers and also for the neurons of the output layer. Now in back propagation, we will move in the backward direction, that is from output to the hidden layer, and then from hidden to the input layer. And during this movement or during this propagation, we will also form the equations. So in the forward direction or in the forward propagation, we learn how to get the equation of OK. So basically, OK is the output of the neural network. It is also the predicted value of the neural network. So OK is the predicted value and TK is the actual value. So the difference between the targeted value, this TK is the targeted value, and OK is the predicted value. So if we find the difference between TK and OK, we will get the error. So that error is obtained during the forward propagation. So during the backward propagation, the error is propagated back through the layers of neural network, and then we update the weights of a neural network so that we can get the improved performance from the neural network. So in the forward direction, we calculate the error. And in the backward direction or in backward propagation, we reduce the error with the help of weight. That is, we update the error, so we update the weights so that the error can be reduced or the performance of a neural network could be improved. So in the first step of a back propagation, we will move from output K to hidden J. So this is our output K and this is our hidden J. So now we are starting the backward propagation or a back propagation, and we will move in the first step from the output K to the hidden J. Okay. In that movement, we will write the gradient equations or the differentiation based equation for the back propagation, and we will update this weight. So basically, if we move in the backward direction from output layer to the hidden layer, it means we have to update the weight between the output layer and the hidden layer, and that weight is WKJ. So basically, we have to reduce the weight, we have to reduce the error with the help of this weight. Therefore, we have to write the equation dE by dWkj, that is rate of change of error with respect to weight Wkj. Since we are moving from output to the hidden, therefore we have to update the weight that is present between the output and the hidden layer. And while updating the weight, we will reduce the error. So now we have to learn how to reduce the error with the help of the weight between the output layer and the hidden layer. Therefore, we need to learn how to write the equation of rate of change of error with respect to Wkj. So this is our neural network. This is the output of the neural network. And we know that after the output of the neural network, which is the prediction of the neural network, we calculate the error by subtracting this predicted value from the actual or the targeted value. So error is somewhere here. So usually we do not show error in neural network. So we know that error is somewhere here after the output of the neural network. So we will start from error. So from error, we will reach to OK. Then from OK, we will reach to net K. And from net K, we will reach to WKJ. So we have three steps. Starting from the error, we will reach to WKJ. this wkj is our parameter which we have to update in order to reduce the error. So in that case, if you see the equation, it has three terms. Why three terms? Because from error to wkj, we have three steps. From error to OK, then from OK to net k, then from net k to wkj. So the equation will be dE by dok. That is, first we will find the rate of change of error with respect to OK. Then we will find the rate of change of OK with respect to net k, and then net k with respect to wkj. So if we move from error to wkj, we need three steps. And for every step, we will write the gradient equation. So here we are using a gradient in the back propagation, and we have three terms when we are moving from the output layer to the hidden layer. Now, the first two terms are called the error signal between the layer K and J. So these two terms may be denoted by a delta K. So we will denote them by delta K, but first we have to find basically these three values. So here we have just written the equation for the back propagation when we move from the output layer to the hidden layer. We see that we need three steps in order to reach from the error to wkj. In that case, we have three terms having the gradients. Now we have to find the value of this term, we have to find the value of this term, and we have to find the value of this term. Now we need to find three values, and after finding these three values, we will put those values here so that we can get the exact value of this gradient, that is rate of change of error with respect to wkj. Let's start by finding the value of dE by dok, or rate of change of error with respect to OK. So I need to find this value dE by dok. Now, what is error? So we know that error is the difference between the targeted value and the predicted value. So this is our error. So here we need to take the first derivative of the error. So with this simple equation, we cannot take the derivative easily. Therefore, we have transformed this error into the square error. So here I am squaring the error, and then I am using half. This half is only for mathematical convenience. Now, what is the mathematical convenience? So mathematical convenience is here when we take the derivative of this E with respect to OK, we can see that this is the derivative. So this is basically like x square. If you treat this whole bracket as x, so this is x raised to power 2, that is x square. So we know that the derivative of x square is 2x, 2 times of x. If we have x square, so its derivative is 2x. Similarly, if we have tk minus ok raised to power 2, we have a derivative 2 times of tk minus ok. So what will happen? We use this half for our mathematical convenience, that when we take a derivative, this 2 will come at the start and this 2 will cancel with this half. In that way, we will get a simplified form of equation. So that was our error. Here we transform the error into the square error. Then we add half. It will become half tk minus ok square. So this is our error to which we have to differentiate it. So this is dE by dok. Here I am taking the first derivative of this error. So 2 tk minus ok, then according to the chain rule, we have to find the derivative of this bracket as well. Since we are differentiating or taking the derivative with respect to OK, therefore the derivative of tk is 0 and the derivative of OK is 1. So if I take the derivative according to chain rule, if I take the derivative of this bracket, it will be 0 minus 1. So 0 minus 1 will be minus 1 only. So this is the derivative of this term, and according to chain rule, the derivative of the term inside the bracket is minus 1. Now this 2 will cancel out. This minus 1 will come at the start and we will left with tk minus ok. So in this way, we have found the value of rate of change of error with respect to OK. So we have calculated the first term in our equation. Now it's time to calculate this second term. Now we know that from the forward propagation, we know that OK is the activation function of net k. So if we use activation function as a sigmoid, then based on the sigmoid equation, this is the equation of OK. So we have OK. Now we have to take the derivative of OK with respect to net K. And we see that inside OK, we have a variable called net K. Now we can easily differentiate this OK equation with respect to net K. So here we are differentiating OK with respect to net K. So the next step will be that we see that in the denominator, we have 1 plus e raised to power minus net k. So we will move this denominator to the numerator so that we can differentiate it. So if we move this whole term to the numerator, it will get minus 1 as a power. So we can see that here we have moved the whole denominator to the numerator. So its power become minus 1. Now it's time to take the first derivative of this term. So according to rule, this minus 1 or any power, if you remember, if it would be x square, then 2 will come at the start. So it is not x square, it is something raised to power minus 1. So minus 1 will come here. Then we have the term. Then we have to subtract minus 1 from the power. It will become minus 2. This is all according to the concept of a differentiation. Then according to chain rule, we have to take the derivative of this bracket. So the derivative of 1 is 0 and the derivative of exponent term is always the same as an exponent term. Then according to rule, we have to take the derivative of the power of the exponent. So since we are taking the derivative with respect to net k, therefore the derivative of minus net k will be minus 1. So in this way, this step shows the first derivative of this term, that is 1 plus e raised to power minus net k to the power minus 1. Now let's simplify it. This minus 1 and this minus will become plus. Then this 0 plus exponent term, we will only get the exponent term. And this term has raised to power minus 2. Now I can move it to the denominator. So it will become plus 2. So after simplification, this term will become this term. Now what we can do, we can see that we have a square here. Since we have a square here, therefore we can split it into two terms. So this is the first term and this is the second term. And here we have add 1 because we know that if we multiply something by 1, it will not change its value. Okay, now what is this? If we see, this is 1 over 1 plus e raised to power minus net k. This term is okay. If we go back, we can see this term is okay. Now, after taking the derivative of this, we can see that this term becomes okay. Now, what we did here with this term? Now, we are left with this term. So, we add plus 1 to this term and then we add minus 1 to this term. So, this term become okay, and to this term, we add plus 1 and minus 1 in order to balance, because we know that we cannot add plus 1 without any reason. So, if we need plus 1, so in order to balance it, we have to add minus 1 as well. So this is okay, and here we have add plus 1 and minus 1. Let's see what we are going to do in the next step. So basically in the next step, we are going to break the LCM. How to break the LCM? This denominator is written both under this term and this term. Let's see what we are going to do. So here we are breaking the LCM. If you see, I am breaking this term separate and this minus 1 separate. So I am separating this term and I am writing denominator under each term. Now what will happen? This will cancel out and I will get 1. And again, if we see this term, it is again okay. So this is the simplification of the term, that if we take the derivative of OK with respect to net k, we will get OK 1 minus OK. So that is our OK. If we see, we started from here. That was our OK. Then we take the first derivative of OK with respect to net k. In order to take the derivative, we move this denominator term to the numerator term. Here we get this form. Then we take the first derivative, this minus 1 come here, and then we subtract minus 1 from the power. It will become minus 2 according to the rule of differentiation. Then according to chain rule, we calculate the derivative of this term, which come out to be this. Then we calculate the derivative of minus net k, which was minus 1. That -1 and -1 will become plus, and by rearranging, we will get this term. Then we split this square into two terms, that is 1 plus e raised to power net k and 1 plus e raised to power net k. Then we replace this term by OK, and then we add +1 and then we subtract -1. Then we break the LCM. So here we are breaking the LCM. This term becomes 1 and this term becomes OK. Now that was the calculation of a second term that was present in our backpropagation equation. Let's move to the third term. Now the third term is we have to find rate of change of net k with respect to wkj. Now where is net k? We basically need net k, equation of net k, in order to take the derivative. We know that this equation net k, which we calculated in the previous lecture where we learn how to write the equation during the forward propagation. So that was the equation of net k. Now here I will put the equation of net k, and here I am taking the derivative. Since the derivative is with respect to kj, therefore the derivative of bk with respect to kj becomes 0. And the derivative of wkj with respect to kj becomes 1. So we are left with only oj. So the derivative of this term will come out to be oj. Now we have calculated all these terms. Now it's time to put the values back. So if you remember, that was the equation of a backpropagation in moving from the output layer to the hidden layer. And now we have calculated the values of each term present in this equation. Now it's time to put the values. So we know that the value of this term is minus tk minus ok. The value of the second term was ok, 1 minus ok. And we have just calculated the value of third term, which is oj. So if we put all these values, we will get the equation like this. And we know that this is our error signal, that is delta k. If we replace these terms by our error signal delta k, we will get this. So finally, we have successfully calculated the rate of change of error with respect to wkj. So this is the gradient of error. Now we have to use this value in order to update the wkj. So here is the updation of wkj. So how to update wkj? So updated value of the wkj will be called as wkj new. That will be the old value. So in order to update the old value, we have to add this term, that is the gradient of error. And we have to associate a learning rate. So here eta, this symbol which is eta, it is known as learning rate. Now it's time to put the values. So this is eta, and we have just calculated this in the previous slide. It is minus delta k oj. So put here minus delta k oj. So plus minus becomes minus, and this will our value of the update. So that is our old weight, and that is our new weight, which is updated by this value. So in this lecture, we learn that during the backpropagation, first we move from the output layer to the hidden layer, and then we move from the hidden layer to the input layer. So in this particular lecture, we only move in the backward direction from the output layer to the hidden layer. First, we write the equation of a backpropagation. We saw that there are 3 derivative terms in the equation of a backpropagation. Then we calculate the values of all these 3 terms. We basically derive the values of all these terms. Then we put those values in that equation, and then we simplify. After simplification, we get the value which is minus delta k oj, and that value will update wkj. So we will use this value in weight updation along with the learning rate. So this is the updated weight of wkj. So in this lecture, we learn how to update the weight using backpropagation if we move from the output layer to the hidden layer. So in the next lecture, we will move from the hidden layer to the input layer. That is the second step of the backpropagation. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this lecture is a continuation of our previous lecture, which was on backpropagation. However, in this lecture, we will cover the step 2 of a backpropagation. That is, we will move from the hidden layer to the input layer, and we will update the weight, which is wji. So let's start this lecture. So basically, we have to update the weight. That weight is present between the input layer and the hidden layer. But we have to start from the error, because the purpose of each weight updation is to remove the error. Therefore, we have to start from the error and we have to reach here, that is the weight which is present between the input layer and the hidden layer. So let's see how many steps we need. If you remember, in the previous lecture, we moved from the output to the hidden layer and we update this WKJ. In that updation, we need 3 steps. That is, we started from error, we move from error to O of K, then net K, and in the third step, we reach here. But here, if we start from the error, which is a necessary step, and if we have to reach up to WJI, which is the weight between the input layer and the hidden layer, we need 5 steps, as you can see here. So this is the equation of rate of change of error with respect to WJI. So basically here we have to reduce the error by updating the weight WJI, which is present between the ith layer and the jth layer, that is between the input and the hidden layer. Okay, let's start from the error and we have to read up to WJI. So here we have an error. So we will move from error to OK. This is our first step. You can see that DE by DOK. Then from OK to net K. So DOK by D net K. Then from net K to OJ. That is, after net K, we will move directly to the OJ. So we will not include WKJ in this equation, because that equation is only for WJI, which is the weight which we have to update. Okay, from net OK, we will move to OJ. Then from OJ to net J, and from net J to WJI. So we can see that from DE by DOK, then DOK by D net K, then this is another gradient, that is D net K over D of OJ. In that way, we start from error and we will reach up to the required weight which we have to update. So here we can see that we need 5 steps. So that is the back propagation for us, that if we are far away from the error. So for those layers which are away from the error, we need more steps in order to reach that weight. So here we have 5 values which we have to calculate. If you remember, in the previous lecture, we had only 3 derivatives or 3 gradient terms. Here we have 5 derivative or 5 gradient terms which we need to update. Okay, let's see how we calculate these 5 values. So luckily, what happened? We have already calculated this value and this value, that is first 2 value, in our previous lecture, that is when we moved from the output layer to the hidden layer. It means now we need only 3 values to calculate. So let's start with D by DOJ of net K. So first of all, we should know what is net K, or what is the equation of net K. So in the lecture of the forward propagation, we learn how to calculate the equation for net K. So that is the equation for net K. Student, if you remember, that is the equation which we obtained during the forward propagation. So we have to take the differentiation of that equation with respect to OJ. Since our variable of differentiation is OJ, therefore this BK is a constant quantity and its derivative will be 0. Similarly, this OJ with respect to OJ will give us a 1. So we are left with only WKJ. So the derivative of this term, or the solution of this term, is WKJ. Next, let first calculate this term, that is the rate of change of net J with respect to WJI. Also in the forward propagation, we learn how to calculate the equation of net J. So that is, student, the equation of net J, that is WJI XI plus BJ. So if you do not remember, you can go back and see the lecture on the forward propagation, where we learn how to write the equation for net K, OK. Also, we learn how to write the equation for net J and OJ. So this is the equation for net J. Here we have to take the derivative with respect to WJI. So the variable of differentiation is WJI. So for this BJ becomes constant and its derivative will be 0. And since our derivative is WJI, so WJI and WJI will give us a 1. So we are left with only XI. So the derivative of this equation with respect to WJI is only XI. So we have calculated these terms, and here we are not calculating this right now, and we will call it F prime of net K. Let's see. Now it's time to put all these values, all the 5 values here, so that we can get the value of rate of change of error with respect to WJI. So the first value is dE. If you remember, the first value is dE by dOk, and second is dOk over d net k. So we know that from our previous lecture. So this value is, the first value is minus tk minus ok, and the second value is ok1 minus ok. Here, for the third value, this is our third value, d net k over oj, and this is our fourth value. So remember, this is our fourth value, this is our third value, wkj is our third value, and this is our fourth value, and this is our fifth value. So now we have already put these two values from our previous lecture. Now for this value we will put wkj, and for the last value we will put xi. So here we have put wkj, and for the last value we have put xi. For the fourth term, we are not going to calculate anything right now. We have just replaced it by the derivative of net j. So basically it is, if we go back and see, this is a rate of change of oj with respect to net j. So basically oj is the activation function, and we have to take the derivative of that activation function. So we are going to represent it by f dash net j. Okay, now these are all the 5 values for the back propagation in order to update the weight wji. So first 4 terms will becomes delta j. So that is the error signal. If you remember, in the previous lecture, the error signal was delta k, and it was these 3 terms which were included in the error signal. So here the error signal is large because we have 5 terms. So if we write this equation in terms of error signal, so we will get minus here. For all these terms, we have delta j, and then we have xi. So this is the value of rate of change of error with respect to wji, and here delta j is the error signal which has this large value, and xi are our inputs. Now, after calculating the rate of change of error with respect to wji, it's time to update the weight. So the weight updation equation is same as we saw in the previous lecture. The new or updated value of ji is equals to the old value plus the learning rate times the gradient of error with respect to wji. Now put this value. So if we know from the previous slide, this is the value minus delta j xi. So put this value here. So we have plus minus minus, we have learning rate, and in place of rate of change of error with respect to ji, we have delta j xi. So in this way, we can see that the updated equations are same for every kind of weight. Only this is the most important term. We use the same learning rate, we use the same equation for update the weight. But this term is important. Every time for every kind of layer, we need to calculate the error with respect to the weights. So in this lecture, we learn how to calculate the weight that was present between the hidden layer and input layer. Since that weight was far away from the error, we observed that we needed to write 5 gradient terms. And it was a big equation which has 5 gradient terms. So we calculate the value of all the 5 gradient terms, we put the value and find the value of rate of change of error with respect to wji, and then we update the weight with the help of the gradient error, learning rate, and with the old value of the weight. So I hope you understood this lecture. I hope you understood now the concept of a back propagation. In the previous lecture, we completed the first step of the back propagation, where we moved from the output layer to the hidden layer and we updated the weight wkj. In this particular lecture, which was the step 2 of the back propagation, we moved from the hidden layer to the input layer and we updated the weight wki. So I hope you understood now fully about the concept of a back propagation and forward propagation. Thanks for listening, and I will see you in the next lecture.